Hello students, in this video we are going to see higher order ordinary differential equations. Higher order. So what is higher order? If a differential equation has order 2 or more, so more than one order is called higher order. So order the differential equation of order 2, order 3, order 4, so 2 and above, everything, all the differential equations are called higher order ordinary differential equations. Okay, so let us see in this unit what we have, what are we are going to learn the topics. Let us see. Okay, the first topic is homogeneous linear differential equations, non-homogeneous linear differential equations with the q of x of the form. So if we observe, 1 second. In second topic, non-homogeneous linear differential equations, there are 5 subtopics. So what is that? The q of x is of the form e power ax, sin bx, cos bx, x power k, and e power ax into v of x power k into v of x. The third topic is Legender's differential equation. Fourth is Cauchy's differential equations. Fifth is method of variation of parameters. Sixth is LR circuits. And last one is simple harmonic motion. Last three, that is method of variation of parameters, LCR circuits, and simple harmonic motions are the applications of differential equations. So differential equation application is in every field, like electronics, mechanical, civil, everywhere we use it. So some of them, only 3 of them here in your syllabus. Okay, method of variation of parameters, LCR circuits, simple harmonic motion. Okay, now let us see the definition of higher order differential equations. What is higher order linear differential equations? It's look like if the differential equations of the form dny by dx power n, p1 of x into dn minus 1, n minus 1th derivative of y with respect to x, p2 of x into dn minus 1, n minus 2 y by dx power n minus 2, and so on. Pn minus 1 x of dy by dx plus pn of y, pn of x into y is equals to q of x. Okay, so this is the bigger differential equation. So this is called higher order linear differential equation, is called higher order linear differential equation if the order is greater than or equals to 2. If the order is 1, so first order linear differential, we call it as first order linear differential equations. Okay, here in this case, the coefficients of derivatives, the first coefficient is definitely 1 anyway, and second onwards we get p1 of x, p2 of x, and so on up to pn of x and q of x. All these are functions of x. All these are functions of x. Okay, so now if the left hand side, the functions p1, p2, so on up to pn, if these are constants, so p1 of x, p2 of x are all constants, then the differential equation is called higher order linear differential equation with constant coefficients. Otherwise it is called variable coefficients. If there's these are functions of x, we call it as variable coefficients. If they are constant, that is p1, p2, so on up to pn are constants, then the differential equation is called linear differential equation with constant coefficients. There are two types of differential equations, with the constant coefficients and with the variable coefficients. Okay, here in this case we shall see the first two topics, that is homogeneous and non-homogeneous. First topic is homogeneous, second topic is non-homogeneous. These two are constant coefficients, where p1, p2, so on up to pn are constant coefficients, whereas Legender's and Cauchy's differential equations are variable coefficients, that is p1 of x, p2 of x, so on up to pn of x are functions of x. Okay, and this is also constant coefficient. Method of variation parameters also constant coefficients. Okay, and now here always in every type, q of x is a function. Even though p1, p2, so on up to pn are constants, but q of x, the right hand side, is definitely a function of x. Okay, and now let us learn how to solve the differential equations. Differential equation, higher order linear differential equations. Okay, and now for first two topics we shall consider p1, p2, and so on up to pn are constants, where q of x is a function of x. The right hand side is as usual the function of x, but the coefficients are constants. Okay, and the bigger differential equation can be written in short form using the operator d. Let us learn what is the definition of operator d. So what is the operator d? So let us define a capital D in the form of d by dx. Just d by dx we write in the capital D. And if it is d square by dx square, d square I'm calling d by dx. It's not dy by dx. It's d by dx. There is no y. Okay, d by dx is capital D. What is d square by dx square? If we define it in short form, we write it as capital D square and so on. That is what is dn by dx power n? Capital D power n, like this and so on. Then the differential equation, the differential operator, capital D is called differential operator or operated. Simply we call it as operated. D is nothing but the derivative operator, differential operator. Okay. And using the operator D form, operator D, we write the bigger differential equation in shorter form and solve it. Okay. How to write in the shorter form? Let us see it. So that shorter form is called operator D form. Operator D form. So the operator D form of a differential equation is, so now given differential equation is this, and if you observe, I'm taking the coefficients p1, p2, so on up to pn are constants. Now I'm not taking like p1 of x. I'm taking just p1 because these are all, let us assume first two topics, let us assume that these are constants, and the right hand side is anyway function of x. Okay. Now, what is dn by dx power n is capital D power n. And y is left here, so we write y also. Okay, d by dx is capital D. So d by dx is capital D, not y. So that's why we have to write dy by dx as dy. And next, dny. And what is the dn minus 1 y by dx power n? dn minus 1 into y. P1 is coefficient. Anyway, P2 is also coefficient. What is dn minus 2y by dx power n? dn minus 2. What is dn minus 2? dn minus 2 by dx power n. And what is extra? Y is extra. So we write y as it is. And so on. At the end also P1 of y. Okay. P1 of y is equal to Q of x as it is. So here in all these terms, what is the common thing? Y is common. So I'm taking y common. So what do we get? dn d power n plus p1 into dn minus 1 plus p2 into dn minus 2 and so on up to pn. And here y is common. So like this, after taking y common, we get like this. Okay, this is, and now in the bracket expression, in the bracket, whatever the expression in the bracket, we take it as f of d, which is nothing but a polynomial in d. If you observe the expression in bracket, which is nothing but a polynomial in d. So I'll take complete the expression as f of d. F of d. Then y as it is, y is equal to f of x as it is. So f of d y is equals to q of x. This form is called operator D form. A bigger differential equation can be written as a short form as f of dy is equals to q of x. So to solve the differential equation, first we write in the operator D form, that is short form and solve it. Okay. This is the way, this is how we can write in the operator D form. Okay. Now let us see what is the difference between homogeneous and non-homogeneous. What is non-homogeneous? What is homogeneous? Let us check it. Okay. So let us define these two terms, homogeneous and non-homogeneous differential equation. This is nothing but if f of dy is equal to q of x is a differential equation. If the right hand side, that is q of x, if q of x is equals to 0, if q of x is equals to 0, that is if we put q of x is equal to 0, what do we get? F of y is equals to 0. Just f of y is equal to 0. This is called homogeneous differential equation. If the right hand side q of x is not equal to 0, that is as it is, f of dy is equal to q of x as it is, which is called non-homogeneous. So here, if q of x is not equal to 0, then f of dy is equal to q of x is called non-homogeneous differential equation. Got it? F of dy is equal to 0 is a homogeneous. F of dy is equal to q of x is non-homogeneous. So that's why here, if you observe the topics, homogeneous linear differential, first of all, f of dy is equal to 0. That is, the right hand side is 0. We shall see the problems related to that. Later in the second topic, we shall see non-homogeneous, where q of x, the right hand side, is of 5 forms. Only 5 forms. We have shortcuts. Okay. Shortcut forms. These are all just shortcut forms. Let us learn all these things. So let us move to the first topic, homogeneous, how to solve higher order differential equations, homogeneous form. So first of all, general form, let us see it. That is non-homogeneous. what will be the solution? Let us check it. Okay, the solution to the higher order differential equation is of the form y is equal to yc plus yp. What is yc? We can also write in the place of yc, we can also write cf. In the place of yp, we can write pi. What is cf? Complementary function. Pi is particular integral. So here I have written cf is complementary function and pi is particular integral. So what is the solution of any higher order differential equation is complementary function plus particular integral. Okay, if I briefly explain what is a complementary function, the complementary function can be found using only f of d. Q of x is not required. Q of x is not required. And particular integral can be found using f of d as well as q of x. We need both of these terms. Okay, then we can find particular integral. So see, how can you find particular integral? Using q of x. So if q of x is equal to 0, particular integrals will also be 0. Particular integral will also be 0. Okay, so that we can see here. So for homogeneous equations, that is f of dy is equal to 0, what will be the solution? Just y is equal to yc. Say here, for any differential equation, the solution will be of the form yc plus yp. Yc is called complementary function, yp is called particular integral. For homogeneous differential equations, so that is f of dy is equals to q of x. F of dy is equals to q of x. The solution is of the form y is equals to just yc. The particular integral will be 0. So here q of x is equal to 0. Q of x is equal to 0. Okay, not q of x. If it is 0, the solution is of the form y is equals to just yc. The yp part will be 0 if the right hand side q of x is equal to 0. The solution will be like this. If it is non-homogeneous, in the case of non-homogeneous, that is f of dy is equals to q of x, then y is equals to yc plus yp. Yp will also be there for non-homogeneous. So first of all, let us learn how to find the complementary function. So let us see how to find the complementary function. That is only, let us take only the homogeneous equations. Okay. Now, if we consider the homogeneous equation, there are 3 steps involved to find complementary function. That is YC. Let us say the 3 steps. Write the given differential equation in the operator D form. What is the operator D form? F of dy is equal to 0. If it is not given in the operator D form, we write in this form. So maximum 95% problems in the exam itself, you get operator D form only. The first step can be skipped if they have given the question in operator D form. Mostly the only 5% chance they may give you in a different form, that is d square by dx square form. Okay, maximum they give you in the operator D form only. Okay, only 2 steps are important. The second step is write the auxiliary equation f of m is equal to 0. What is f of m is equal to 0? So here f of dy is equal to 0 now. Here just remove y and in the place of d put m. So in the place of d put m, f of d becomes f of m and y we remove it, then f of m is equal to 0. That is the polynomial in d, we write in the polynomial in m. In the place of d put m. So this is a polynomial in m. So this is called auxiliary equation. So next we find the roots of the auxiliary equation. Using the roots, we write the complementary function. Using the roots of the polynomial. First, we find the roots of the polynomial. Okay. So we can find the roots using calculators or some other way we can find it. Okay. Now, let us assume that f of m is of nth order. Nth degree. So the polynomial is of nth degree. If the differential equation is the nth order, then the polynomial will be in nth degree. If it is nth degree, how many roots we get? N roots. We get n roots. So in the first case, there are 5 cases about the roots. The roots can be distinct and real and distinct, real and equal, and complex. They can be complex. Based on these conditions, we can divide the roots in the form of 4 cases. Let us see about the first case. If the roots are real and distinct, that is m is equal to m1, m2, so on up to mn all are real and distinct. Real means -1, -2 are positive or negative, only integers. So only integers. Then yc can be written as yc is equals to c1 e power m1x, c2 e power m2x, and so on up to cn e power mnx. C, the arbitrary constant e power x is common. So just we write the roots m1, m2, so on up to mn in the powers of exponential function. So e powers. E powers, we write all the roots. That's very simple. We can write it. So if we observe, what about C1, C2, so on up to Cn? These are all called arbitrary constants. Arbitrary constants. So if f of m, f of dy, if the differential equation is of second order, how many arbitrary constants we get? Only two, C1 and C2. If the differential equation is third order, we get three arbitrary constants like this. So whenever we get, if the order is three, we get three roots. Based on three roots, we get only three arbitrary constants. And so if the first case is real and distinct, the second case, if the second case is the first two roots are equal, the first case is real and distinct, all are distinct, different roots. But here in the first two roots are equal, that is m2 is nothing but m1. M2 is equals to m1. That is first two roots are what? M1, M1, M3 onwards real and distinct. M3 onwards real and distinct. So we consider only first two terms. First two terms, that is M1. So if the two roots are equal, we write C1 plus C2x into e power M1x. M1x. Third root onwards is the same as usual in the previous case. C3 e power M3x plus and so on Cn e power Mnx. If two roots are equal, we write in the form of C1 plus C2x into e power the equal root, that is M1x. The third case, if three roots are equal, first three roots are equal, that is M2 is equal to M1 as well as M3 is also M1. So M1, 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 and fourth root onwards real and distinct. Fourth root onwards, that is real and distinct. Then, so how do you write? So C1 plus C2x plus C3x square into e power M1x. So we write in the form of like this, first three roots. The fourth root onwards, it's same, common. Okay. And let us check the fourth case. I told you, there are five cases. First three cases real, distinct and equal we have seen. But fourth and fifth are complex roots. So when it comes to, if the roots are complex, we may get complex roots also. If the first two roots are complex conjugates and the remaining are real and distinct. And the remaining are real and distinct. First two roots are complex conjugates. That is m is equals to. So here the first root is, if you observe, the first root is m1 is equals to a plus bi, m2 is equals to a minus bi. So combinedly we write a plus or minus bi. This is complex conjugates. So this is complex, this is also complex. Combinedly, if what's the conjugate of this one? A minus bi. What's the conjugate of a minus bi? A plus bs. That's why these combinedly we call it as complex conjugates. If first two roots of complex conjugates, that is m is equal to a plus or minus bi, and m3 onwards real and distinct as usual. Okay? Remember, if we get a plus bi as the root, if we get a plus bi as the root, then definitely we get a minus bi is also another root. Definitely. We cannot get the root a plus bi alone. Okay, we cannot get a minus bi alone. So we get combinedly a plus or minus bi. So if the first roots are complex conjugates, what do you write? First two arbitrary constants we write like this: c1 cos bx plus c2 sin bx into e power ax. E power ax. If you observe, we substitute only three substitutions: b, b, a. B two times, a one time. A is the real part, B is the imaginary part. From the complex roots, we take the real part and we write in the exponential e power ax. And we take the imaginary part, B, we write cos bx, sin bx. Cos bx, sin bx. If we take an example, suppose if we get 2 plus or minus 3i, 2 plus or minus 3. Here, what's the real part is 2 and imaginary part b is equals to 3. So how do you write? C1 cos bx, what is b? 3x plus c2 sin bx, what is b? 2, actually 3x, and whole into e power 2x, whole into e power 2x. So like this we write. From third root onwards, real and distinct. So we write C3 e power m3x plus and so on Cn e power mnx. Like this we write if the roots are complex. And if we go to the fifth case also complex but equal complex roots. First four roots are complex conjugate, equal complex conjugates. That is, if m1 is equals to a plus bi and m2 is equals to a minus bi, m3 is also a plus bi, m4 is also a plus a minus bi. Then we get a plus or minus bi, comma a plus or minus bi. So equal complex conjugates, four roots, equal complex conjugates. That is a plus or minus bi, comma a plus or minus bi. Four roots over. Fifth onwards, fifth root onwards, real and distinct. Just assume real and distinct. Then yc is what? So c1 plus c2x into cos bx plus c3 plus c4x into sin bx e power ax. Here also only three substitutions. B 2 times and a 1 time. Remaining everything is same in every problem. We take the real part and write here e power ax. We take the imaginary part, we write in the cos and sin. Remaining everything is same. C1, C2, C3, x, everything is same. The plus fifth root onwards is common. C5 e power m5x plus and so on Cn e power mnx. So here M1, C1, C2, so on of this are arbitrary constants. How many arbitrary constants we get? Depends on the order of the differential equation. Depends on the order of the differential equation. Okay, this is about the introduction of complex complementary function. So let us see the first topic, that is homogeneous differential equation f of dy is equal to 0. In the next class, so let us see how to write those roots and everything, and we shall see the next topic. This is just an introduction. This video is just an introduction of this unit, higher order differential equations. The next video I'll explain homogeneous differential equation. That is, we shall learn how to write the solutions of homogeneous differential. That is YC complementary. Let us learn complementary functions. Okay.